Welcome to this rigorous scientific exploration of one of the most fundamental techniques in culinary science, finishing sauces with cold butter. Over the next 15 minutes, we'll dive deep into the physics and chemistry that make this technique so transformative. When chefs finish a sauce by whisking in cold butter at the end of cooking, two remarkable things happen. The sauce becomes noticeably glossier, with a beautiful sheen, and it becomes thicker and more viscous. But why does this happen? What are the physical and chemical mechanisms at work? First, we observe a dramatic increase in glossiness. The sauce goes from matte to having a mirror-like sheen. Second, the viscosity increases. The sauce coats a spoon more effectively and has a richer mouthfeel. Third, and this is critical, the butter must be cold. If you add melted butter, you don't get the same effect. This tells us something important about the mechanism. To understand this phenomenon, we first need to understand what butter actually is at a molecular level. Butter is approximately 80 to 82% fat and 16 to 18% water, with small amounts of milk proteins and natural emulsifiers like lecithin. At room temperature, butter is a water and oil emulsion. The water is dispersed as tiny droplets throughout a continuous fat phase. This is crucial. Butter is a water and oil emulsion, where water droplets are suspended in fat. This is the opposite of what we'll create in the sauce. Now let's think about what happens when we add cold butter to a hot aqueous sauce. The sauce is primarily water-based, perhaps with some wine, stock, or cream. Here's a question to consider. What happens to the butter's structure when it meets the hot sauce? The answer involves mechanical shearing. As we whisk the butter into the sauce, we're applying mechanical energy. This breaks the butter into smaller and smaller pieces. We start with a water-based sauce and solid cold butter. Through whisking, we create an oil and water emulsion, where fat droplets are now dispersed in the aqueous phase. This is the exact opposite of butter's original structure. The core process here is emulsification. An emulsion is a mixture of two immiscible liquids, where one liquid is dispersed as droplets in the other. An emulsion consists of a dispersed phase, which forms the droplets, and a continuous phase, which surrounds them. In an oil and water emulsion, which is what we create when we monte beurre, fat droplets are dispersed in an aqueous continuous phase. The opposite, water in oil, is what butter originally is, water droplets suspended in fat. Now let's consider the thermodynamics. Emulsion formation is not spontaneous. It requires energy input. The change in Gibbs free energy equals gamma, the interfacial tension, times delta A, the change in surface area. When we break butter into tiny droplets, we're creating an enormous amount of new oil-water interface. This requires energy, which we provide through whisking. The interfacial tension between oil and water is about 20 to 30 millinewtons per meter. This acts to minimize surface area, which is why emulsions want to separate. Let's do a quick calculation to see how much surface area we create. Let's say we add 50 grams of butter to 200 milliliters of sauce. That's about 3 tablespoons of butter. The volume of fat is 50 grams divided by the density of butter fat, which is about 0.92 grams per milliliter. This gives us 54 milliliters of fat. In a well-emulsified sauce, the fat droplets are typically around 1 to 5 micrometers in diameter. Let's use 2 micrometers as our estimate. The number of droplets equals the total fat volume divided by the volume of one droplet. Using the formula for sphere volume, we get approximately 13 trillion droplets. The total surface area is the number of droplets times the surface area of each droplet. This gives us about 2 square meters of oil-water interface. That's remarkable. We've created roughly 2 square meters of oil-water interface in just 200 milliliters of sauce. This massive interfacial area is key to understanding both the glossiness and the viscosity increase. Now, you might ask, if oil and water don't want to mix, how do we stabilize this emulsion? The answer is emulsifiers. Here's an important question. Given that oil and water naturally separate, why doesn't our sauce immediately break? The answer is that butter contains natural emulsifiers, particularly milk proteins and phospholipids like lecithin, that stabilize the emulsion. Emulsifier molecules are amphiphilic. They have a hydrophilic head that loves water and a hydrophobic tail that loves fat. At the oil-water interface, they orient themselves with heads in water and tails in oil. By occupying the interface, emulsifiers reduce the interfacial tension from about 30 millinewtons per meter down to around 10 millinewtons per meter or less. This makes emulsion formation much easier and stabilizes the droplets. Now let's address the glossiness. Why do millions of tiny fat droplets make the sauce glossy? Glossiness is fundamentally about how light interacts with the surface of the sauce. A glossy surface reflects light in a specular manner, like a mirror. On a rough surface, light scatters in all directions, giving a matte appearance. On a smooth surface, light reflects at consistent angles, creating a glossy appearance. The tiny fat droplets create what appears to be a smooth optical interface. The droplets are much smaller than the wavelength of visible light, which is 400 to 700 nanometers. Our 2-micrometer droplets are about 3 to 5 times larger than the wavelength of light, but they're still small enough that the sauce appears homogeneous to light. The wavelength of light is approximately 500 nanometers. Our droplet diameter is approximately 2,000 nanometers or 2 micrometers. Butterfat has a refractive index of about 1.46, while water is 1.33. This difference in refractive index affects how light reflects from the surface. The refractive index of fat is 1.46. The refractive index of water is 1.33. The key is that a uniform dispersion of fat droplets creates a uniform refractive index throughout the sauce, leading to consistent light reflection and that characteristic gloss. Now let's tackle the viscosity increase, which is arguably more interesting from a fluid mechanics perspective. Here's a fundamental question. Why does adding fat droplets to a water-based sauce increase its viscosity? After all, butterfat itself has relatively low viscosity. The answer comes from Einstein's work on suspension viscosity. Even dilute suspensions of particles increase viscosity. Einstein showed that the viscosity eta equals the base fluid viscosity eta 0 times the quantity 1 plus 2.5 times phi, where phi is the volume fraction of particles. This equation applies to dilute suspensions of non-interacting spherical particles. Let's calculate what this predicts for our sauce. The volume fraction phi equals the fat volume divided by the total volume. That's 54 milliliters divided by 254 milliliters, which equals 0.21 or 21%. Using Einstein's equation, we predict the viscosity should be 1.53 times the original viscosity, a 53% increase. However, in practice, we often see larger viscosity increases than this. Why? Because Einstein's equation assumes dilute, non-interacting particles. At volume fractions above about 0.1 or 10%, we need to consider droplet interactions. At 21% volume fraction, our droplets are close enough that they begin to interact hydrodynamically. They affect each other's flow. For more concentrated suspensions, we need higher order terms. The Bachelor equation includes a phi squared term. ETA equals ETA E0 times 1 plus 2.5 phi plus 10.05 phi squared. With the phi squared term, we get 1 plus 0.525 plus 0.44, which equals 1.97. Now we're predicting almost a doubling of viscosity, which is much closer to what we observe. Beyond just viscosity, the fat droplets profoundly affect mouthfeel, which is how the sauce feels in your mouth. Fat droplets create what we perceive as creaminess. This isn't just about viscosity, it's about lubrication and texture. The tiny fat droplets act like microscopic ball bearings, providing lubrication between the tongue and the palate. This creates a smooth, creamy sensation. Between the tongue and palate, fat droplets reduce friction. They create a lubricating layer that gives the sensation of richness and smoothness. Additionally, fat is an excellent solvent for many flavor compounds. The fat droplets trap and carry aromatic molecules, releasing them slowly as the sauce is consumed. Now let's address a critical practical point. Why must the butter be cold? Why doesn't melted butter work as well? This is a key question. If we're just creating an emulsion, why does the temperature of the butter matter? The answer relates to how the emulsion forms. Cold butter provides a controlled release of fat. When you whisk cold butter into hot sauce, it melts gradually. This gradual melting allows for better control of droplet size formation. As the butter softens and melts, the mechanical action of whisking breaks it into fine droplets. The still solid portions help create smaller droplets through a kind of grinding action. With cold butter, the gradual melting produces fine droplets with high surface area. With melted butter, the fat mixes rapidly but forms larger droplets with less total surface area. Cold butter emulsification produces droplets around 2 micrometers. Melted butter tends to form droplets around 10 micrometers or larger. Remember, surface area scales inversely with droplet diameter. Smaller droplets mean much more surface area. The ratio of surface areas equals the inverse ratio of diameters. So cold butter creates about 5 times more surface area than melted butter for the same volume of fat. This greater surface area is why cold butter produces a glossier, more viscous sauce. It's all about maximizing that oil-water interface. Let's dig a bit deeper into the phase behavior of butterfat with temperature. Butterfat isn't a pure substance. It's a complex mixture of triglycerides with different melting points, ranging from about -40 degrees Celsius to +40 degrees Celsius. The melting range spans from -40 degrees Celsius to +40 degrees Celsius. At refrigerator temperature, around 4 degrees Celsius, butter is mostly solid with some liquid fat present. At room temperature, around 20 degrees Celsius, butter becomes plastic. It's soft and spreadable but still maintains some structure. Above about 35 degrees Celsius, butter becomes fully liquid as all the triglycerides have melted. Here's a schematic of butter's phase behavior. As temperature increases, the fraction of liquid fat increases gradually. This is why butter has such a wide, useful temperature range. We should also discuss emulsion stability. How long does this beautiful emulsified sauce last? An important question for any cook. Will this sauce break? Will the fat separate out? The answer is yes, eventually. But if the emulsion is well made, it can remain stable for 15 to 30 minutes or longer, which is sufficient for service. One destabilizing mechanism is Ostwald ripening, where larger droplets grow at the expense of smaller ones due to differences in Laplace pressure. The Laplace pressure, delta P, equals 2 gamma divided by R, where R is the droplet radius. Smaller droplets have higher internal pressure, which drives fat molecules to diffuse toward larger droplets. Another mechanism is creaming. Fat droplets are less dense than water, so they tend to rise to the surface over time. The creaming velocity versus equals 2r squared g times the density difference divided by 9 ETA, where ETA is the viscosity. Notice that velocity scales with r squared. Smaller droplets cream much more slowly. A 2 micrometer droplet creams 25 times slower than a 10 micrometer droplet. Let's compare butter-finished sauces to cream-based sauces to highlight the differences. A Beurre Blanc is essentially a pure butter emulsion stabilized by very little, besides shallots and wine reduction. It's delicate and can break easily if overheated. Cream-based sauces benefit from casein proteins that act as powerful emulsifiers, making them much more stable. A butter-finished sauce falls in between. The base sauce provides some stability, and the butter adds richness and body. Here's a comparison. Beurre Blanc is highest in fat, but most delicate. Butter-mounted sauces are intermediate. Cream sauces are lowest in fat, but most stable due to protein stabilization. Let's translate all this science into practical guidelines for the kitchen. First, always use cold butter directly from the refrigerator. This ensures gradual melting and fine droplet formation. Second, whisk continuously. You need to provide mechanical energy to break up the butter into fine droplets. Third, add the butter in small pieces. This allows each piece to emulsify before adding more, giving better control. Fourth, maintain the sauce temperature between 50 and 70 degrees Celsius. Below 50, the butter won't melt properly. Above 70, the emulsion becomes less stable. The optimal temperature range is 50 degrees Celsius, less than tea sauce, less than 70 degrees Celsius. Fifth, remove the pan from direct heat once you begin adding butter. The residual heat is usually sufficient. Sixth, serve the sauce as soon as possible. The emulsion is most stable and attractive immediately after formation. For those interested in more advanced rheology, butterfinish sauces often exhibit shear-thinning behavior. Shear-thinning means that the viscosity decreases as you apply more shear. The sauce flows more easily when stirred or poured. This can be described by the Carreau model, where viscosity depends on shear rate gamma dot. At low shear rates, viscosity is high. At high shear rates, viscosity decreases. This shear-thinning behavior contributes to the luxurious mouthfeel. The sauce coats the tongue but doesn't feel thick or gloopy. At high shear rates, the droplets can deform from spherical to ellipsoidal shapes, which affects flow properties. Let me summarize the key scientific principles we've covered. Whisking cold butter into hot sauce creates an oil and water emulsion, with millions of tiny fat droplets dispersed in the aqueous phase. These droplets, typically 1 to 5 micrometers in diameter, create enormous surface area on the order of square meters per cup of sauce. This large interfacial area creates a uniform optical interface that reflects light specularly, producing glossiness. The suspended droplets increase viscosity through hydrodynamic interactions, roughly doubling the viscosity at 20% fat volume fraction. Cold butter is essential because gradual melting allows formation of much finer droplets than melted butter, maximizing surface area and effect. Droplet size affects both emulsion stability through Ostwald ripening and creaming, and mouthfeel through lubrication and creaminess perception. Let me give you some quantitative benchmarks to remember. Droplet size in a well-made emulsion, 1 to 5 micrometers. Surface area created, approximately 2 square meters per cup of sauce. Viscosity increase, typically 2 to 3 times the base sauce viscosity. Optimal sauce temperature, 50 to 70 degrees Celsius. Emulsion stability time, 15 to 30 minutes before noticeable separation. Finally, let's consider why this technique remains so important in fine dining despite its technical challenges. First, the glossiness achieved with a proper butter mount is unparalleled. No other technique produces quite the same visual appeal. Second, the mouthfeel is luxurious without being heavy. The fine emulsion provides richness and body without the cloying heaviness of cream. Third, butter enhances and carries flavors in a unique way. Fat-soluble flavor compounds dissolve in the butter droplets and release gradually. Fourth, executing this technique properly demonstrates technical skill and attention to detail, which is valued in fine dining. In conclusion, the butterfinish sauce represents a beautiful intersection of science and culinary craft. The physics involves emulsification, fluid rheology, interfacial phenomena, and optics. The chemistry involves lipid phase behavior, amphiphilic molecular interactions, and the complex composition of butterfat. The technique requires precise temperature control, appropriate mechanical energy input through whisking, and timing. The result is a sauce that delights all the senses, visually glossy, texturally luxurious, and a perfect vehicle for flavor. Understanding the underlying science doesn't diminish the craft. Rather, it deepens our appreciation for this elegant technique and helps us execute it more consistently and successfully.